Okay, thank you for coming to our third learning workshop. In this learning workshop, we're going to be covering moles and empirical and molecular formulas. So, first question we want to start off with is, what is a mole? Have you talked about moles in class yet? Does anybody have an idea? And feel free to turn on your mics and speak freely. It's more fun if it's conversational. If you don't have a situation, or if you don't have a mic, or if it's loud where you are, if you want to not use your microphone, that's totally fine as well. You can type into the chat. Otherwise, you are definitely more than welcome to have a hot mic, so to speak, an active microphone.
Yes, in fact, the more the merrier, as they say.
So what is a mole? Any ideas?
Is it the element's atomic mass?
Oh, I couldn't quite make out that. Did you hear that, Dr. Neely?
No, it was, I also had a bit problem with the sound coming in, sorry.
Elements atomic mass. Oh, gotcha. No, not quite. So we have a problem in chemistry. Anybody else want to take a stab at it? Because the mole is really kind of a quirky concept. It's not something that's totally obvious.
So I was thinking it's like a uniform collection to categorize like a whole bunch of different stuff, because the stuff you're trying to categorize isn't uniform. So
Yeah,
I don't know.
no, that's not a bad idea. And actually, you're hitting on something there, because the mole of a gas, any gas, and this is where Avogadro got the idea for a mole. He's studying gases, and he determined that a mole of any gas occupies the same volume regardless of what it's composed of. A mole of particles in the gas phase occupies the same volume regardless of what it is. And that comes down to, what the heck is a mole? Well, let's break that down. Essentially, a mole is a number, or as we like to sometimes joke around, we say a mole is what can be referred to as a chemist's dozen. So, a chemist's dozen. It's not really, you heard of a baker's dozen is like 13. So we say a mole is like a chemist's dozen. Well, here's the thing. A mole is not actually a dozen. A mole is simply a number. It's a number like a dozen. And let me go ahead. Oh, there we go. I like that color. Okay, so basically ooh, that's really fat. I don't want to be that fat. Okay, a mole is a specific number, and in particular, the number happens to be 6.022 times 10 to the 23rd. Okay, a mole is 6.02 times 10 to the 23rd. Now, you might say, well, 6.02 times 10 to the 23rd, what? Well, that depends. If you have a mole of pennies, it's 6.02 times 10 to the 23rd pennies. If you have a mole of donuts, it's 6.02 times 10 to the 23rd donuts. So a mole of atom, however, this number is so big. It's 602 hexillion. 602 hexillion. So that's 1, 2, 3. Just to give you an idea of how incredibly big this number is.
And to reiterate what Professor DePaul was saying when he initiated this workshop, there is a reason why we like to use the mole. If you recall, that one proton weighs 1.67 blah 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 1.67 something times 10 to the minus 24 grams, which is an extremely tiny number. So we want to work on a more manageable scale, the AMU. And if you also recall the definition of an AMU, the mass of one carbon-12 is exactly 12 atomic mass units, but we still cannot measure that out in lab. So we use the simplifying concept, the mole. Just like Professor was talking about the dozen number. So for example, we are used to saying 1 dozen eggs. Oops, no, I don't want to use eggs. I'm vegan. So let's say 1 dozen apples. So it means 12 apples, or 1 gross of pencils means 144 pencils. So it's, so you were talking about the huge number. Please go ahead. Thanks.
Okay, so yeah, basically the idea is this. Um, when I have like a chemical equation, so let's say for example, H2 plus O2, so hydrogen plus oxygen goes to form water. And I write the balanced chemical equation here. And you may not have covered balanced chemical equations, but I'll just go ahead and show you here. So 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. Now here's the problem. You might think, well, 2 grams of hydrogen, does that react with 1 gram of oxygen to form 2 grams of water? Well, no, not at all, actually. This is not correct. Because the problem is that different atoms weigh different amounts. Hydrogen, for example, was the lightest element. And because it was the lightest element, it was given the generic number, the generic weight, or the which is the relative weight, the relative atomic weight. Because keep in mind, obviously we can't weigh an atom, right? You can't put an atom on a scale. But we noticed in how these things reacted that there is a certain ratio, and that based on those ratio, they determined how heavy some elements were compared to how heavy other elements were. Since hydrogen was the lightest one, that's why it has a mass of 1. And helium was the next lightest one, but it was twice as heavy. And so that's why it has a mass of 2. And so on and so forth. It turns out that oxygen had a mass of 16 times that of hydrogen. So oxygen was given the relative mass of 16. Okay, so now where does all this come in? Well, these relative masses are great, but we need to find a way to connect relative masses to actual tangible masses. So for example, I need to figure out, okay, if I have, let's say, a measurable amount of hydrogen gas, let's say I have 1 gram of hydrogen, okay? I need to know how many particles that is. How many atoms of hydrogen is that? Well, through some really interesting experimentation and calculation, Avogadro discovered that the relationship between 1 gram of hydrogen gas and the number of particles was this: 6.02 2 times 10 to the 23rd. So 6.02 times 10 to the 23rd atoms of hydrogen equaled its atomic mass, or its relative atomic mass, but in grams. And as a result, this number, 6.02 times 10 to the 23rd, actually does the same thing for every other element. 1 mole of any substance, like in terms of the atomic mass in grams of any substance, is equal to their molar mass, or their atomic mass in grams. The molecular mass or the atomic mass. So if we're talking about atoms, we say, well, the atomic mass of hydrogen is 1, so 1 gram is equal to 6.02 times 10 to the 23rd atoms of hydrogen. If we're talking about water, so the molar mass, or the relative atomic mass of water is about 18 grams of H2O, because hydrogen has a mass of 1, oxygen has a mass of 16. So there's 2 hydrogens. 2 plus 16 gives you 18. 18 grams of water is 6.02 times 10 to the 23rd molecules of water. So what Avogadro basically did is he discovered the key relationship between macroscopic weights and the number of particles that they represented. The beyond microscopic, unseeable particles. How many of them were there? So, depending upon if you're talking about now let's say molecular mass or atomic mass, I'm talking about in grams. So that leaves us with these over here, this relationship over here. So 1 mole of any substance, when we're talking about a chemical substance, a mole simply means 6.02 times 10 to the 23rd, but 1 mole of a chemical substance, when you say 1 mole of water or 1 mole of hydrogen, that's going to be 6.022 times 10 to the 23rd atoms or molecules. Now, if it's atoms of hydrogen, then that's a mole of hydrogen. Or if it's molecules of water, then that's a mole of water. 1 mole, as I also mentioned up here, 1 mole is also equal to the mass or the atomic or molecular mass in grams.
I wanted to write something here, but for some reason my pen is inactive. So on this line, on the above line, 1 mole is equal to 6.022 times 10 to the 23rd atoms or molecules. Could you please write in parentheses particles? So particles would just be inclusive of.
Gotcha.
Thank you.
Does that make sense? Any questions over that? Sorry for that random piece there. Cool.
So
Okay.
Elaine is asking, oh, the chat came and it left. I saw the chat and it just disappeared.
Oh, no problem. I got it. So yeah, is the atomic and molecular mass the same as the molar mass? Okay, so yes and no. Okay, so to kind of give you, so that's a really, really good question. Let's give you a little bit of a framework, and I'm concerned that maybe what I wrote here is making things a little bit confusing. So I'm going to just drop that. But to answer Elaine's question, let me explain this a little bit. Okay, so here's the deal. There is a difference. Essentially, what it comes down to is this. Let's see, the atomic mass I'll use the atomic mass as an example, of hydrogen is 1 AMU. And that is the mass of 1 atom. Mass of 1 atom. And an AMU is like 1.0 something times 10 to the negative 30 something. Or no, 10 to the negative like 20 something kilograms. 24
Yes.
kilograms or something like
Yes,
that. So it's a really, really, really tiny mass, 1 AMU,
right.
atomic mass unit. So this is a mass of 1 atom. However, if you multiply the AMU by 6.02 times 10 to the 23rd, you get the molar mass. So the molar mass of hydrogen So I was being a little bit lazy in my designations earlier. I apologize for that. But the molar mass of hydrogen is 1 gram. Notice it's the same number, but AMU refers to the mass of one single hydrogen atom, whereas gram refers to the mass of a mole of hydrogen atoms. So 1 gram is literally 6.02 times 10 to the 23rd times what an AMU is. Does that make sense?
So yes, bottom line, a very good fundamental question, distinguishing between the mass of one atom versus the mass of 1 mole of hydrogen atom.
Yep. So yeah, molar mass and molecular mass are the same number. It's just one refers to the molecule, the other refers to the a mole of the molecule. And in like atomic mass and molar mass, one refers to the mass of a single atom in AMU, and the other refers to the mass of a mole of atoms. And the number is the same. It's just the unit that's different. It's different. So let's take a look at some calculations. Dr. Neely, you want to go ahead and show them how it's done?
Sure. Let me ask you this, Professor DePaul. When I okay, so I put my pen on the squiggly line,
Uh-huh.
and then I put my stylus pen on the screen. It does not write.
So interestingly enough, for some reason, it looks like only one student is still connected to the whiteboard, at least for me.
Ah.
So you must have accidentally disconnected, or some. Yeah, there you go. I got another student just came back and reconnected. So I don't know why that is, but that's okay. We can go ahead and start. Um, and you can take over as soon as you got everything working. How many
Sure.
atoms are in 2.4 moles of boron? So as with all conversions, we're going to start with our given. We're given 2.4 moles of boron, moles of B. And then we're going to multiply times a conversion factor, which is a fraction, where the top is equal to the bottom. Now, once again, emphasizing the skills we learned before when you're doing conversion factors, follow the units. Follow the units. The units first before any numbers are put down. So what unit goes down on the bottom of this first conversion factor?
Moles.
Absolutely, moles. And so, yeah, every measured value is composed of two parts, a number and a unit. The unit tells you what type of measurement you have, and the number tells you the quantity. So moles of B goes on the bottom. Now I'm trying to convert to atoms. Can I relate moles directly to atoms? What do you think?
Yes, it just has to be 6.022 times 10 to the 23rd, right?
Yeah, absolutely. I recognize the relationship between moles and atoms is Avogadro's number. 1 mole is equal to the 6.022. Ah, 022, sorry. Pardon my terrible handwriting. Times 10 to the 23rd. Okay, so I got 6.022 times 10 to the 23rd atoms of B is equal to 1 mole of B. And this is just going to be a one-step conversion, so this is not going to be too hard. I just multiply the top and divide by the bottom, and I get my answer. Now, when you're entering this into the calculator, you may want to enter this in as, you may want to write this as 6.022E, or in your calculator, it might actually say EE, but 6.022E 23. So that's the way your calculator might read it. 6.022 times times 10 to the 23rd is the same as typing in your calculator 6.022 exponent or E23 and multiply that times 2.4. And what do we get? 1.445? Yeah, and with this, and that sounds about right. The only thing that I would say here is that the number of sig figs you start with has to be equal to the number of sig figs you end with. So Elaine is absolutely correct. You have to watch your sig figs. You only have 2 sig figs to start, and so we're only going to have 2 sig figs in our final answer. And so basing the 1. So that would be 1.4 times 10 to the 24. 1.4 times 10 to the 24. And now the atoms of boron. Cool. So, let's separate this. Okay. So now let's take a look at the next one. This is how many moles are in 1.87 times 10 to the 25th molecules of sugar. Now, let me ask you this question. Do we need to know what the formula for sugar is to solve this problem? What do you think?
No, we do not. Since we know how many molecules there are, you can just divide by the number, I think.
Good
You're
job.
absolutely right. In this case, we do not need to know. If we wanted to solve for the grams of sugar, then we would. But in this case, we only need to know the moles of sugar, so we can actually just go from molecules straight to moles. Because remember, it would just be like if I was converting something to dozen. 12 of anything is equal to a dozen. 6.022 times 10 to the 23rd of anything equals a mole. So I can just go 1.87 times 10 to the 25th molecules is equal. I'll multiply that times my conversion factor. And the unit on the bottom is going to be molecules. Whatever was previously on top always comes in the bottom. And then I'm going to convert that to moles. Just like Ethan said. So 1 mole is equal to Avogadro's number. So 6.02 times 10 to the 23rd molecules is equal to a mole. By the way, is my handwriting legible? Can you read what I'm writing?
Yes, sir, I'm good.
Okay. Awesome. Okay. So then we just divide that, and what do we get? Yeah, oh, yes, Rosanna. Grams, if you wanted to convert to grams, you need to know what the formula is because you can only calculate the molar mass with the formula. If you don't have the formula, you can't calculate the molar mass and you can't convert to grams. But if you're just going from molecules to moles, then you don't need the formula because it's just the number of particles to mole. Does that answer your question? Sorry, I didn't notice your question earlier. Okay, awesome. Okay, excellent. So I get 31.1, and very wisely you chose 3 significant figures, which is great because that's exactly what it should be. And you end up getting about 31.1, which is right on target. So excellent job. Well done, everyone. All right. Coincidentally, if you did not get that number for any reason, like if you did not get the x, like if you got a weird exponent or something, one of the things that you should that you should maybe attend to is when you're dividing by a number in scientific notation, you have to make sure that you use parentheses. If you don't use parentheses when dividing by this, the answer will not come out right unless you use the EE button. So use the EE button or use parentheses. So just be careful when you're dividing by a number in scientific notation.
And the easiest way when you're using your calculator on these numbers is to just go ahead and punch the EE button. It really simplifies everything.
Yeah, that's true. So now it says how many grams are in 7.89 moles of NaCl? Okay, so I have 7.89 moles, and I'm going to convert this moles of NaCl. I'm going to go ahead and convert this to grams. So what unit's going to have to go on the bottom?
Moles.
Yep, moles of NaCl. Don't forget to put what it is too. Don't just put moles of NaCl. Okay, and what can we convert moles of NaCl to? Can we convert to grams directly?
Yes.
Yes, yes indeed we can. But to do so, we need to know what the number relationship is. How do you figure out how many grams is in a mole?
Divide by the molar mass.
Well, not necessarily divide by the molar mass, but you need to calculate the molar mass.
Oh.
And where do you get the molar mass from?
Find the atomic mass.
Yeah, so where do you get the molar mass from?
I can't remember.
And don't say Google it. I know you could, but molar mass of NaCl. It would tell you. It would tell you too. But you actually have to look at the periodic table. So the number underneath each of the elements in the periodic table tells you their mass. So for something like NaCl, I can see that I have one sodium atom, and I have one chlorine atom. So I'll take one atom times the molar mass of sodium, which is 22.99. And then I'll take one chlorine atom and multiply that times the molar mass of chlorine on the periodic table, which is 35.45. And yes, I have those memorized because I'm a super big nerd. And nothing better to do, apparently. So 22.99 and 35.45. And if I add those together, that's going to give me 58.44. Now, do you have to write this all out like this? No, you don't. Absolutely not. You can actually probably do it in your head or in a calculator. But I might recommend, at least early on, especially for the more complicated molar masses, of writing them out just to kind of get a clear idea in your head of what you're doing with them. So now that I know that this is 58.44, this is 58.44 grams per mole. That means for every 1 mole of sodium chloride, I'm going to have 58.44 grams. So then I multiply everything on top and divide by the bottom. And what does that give me? Nope, doesn't give me that.
Give it another whirl.
Yeah, give it another roll. That's a good idea. You put 6.02 times 10 to the 23rd on bottom, didn't you?
Yes, I did. Yeah, unfortunately.
Yeah, no, so there you go. That sounds a little bit more like it. So 461 grams. It's a pretty big amount. A mole is nothing to sneeze at. 461 grams, that's basically about a pound of salt. That's a pound of salt. A Costco container of salt. So there you go. All right, so now that's how you do it. So if you're going from molecules to moles, you can use the Avogadro's number, or atoms to moles, you can use Avogadro's number. But if you're going from moles to grams, you have to use the molar mass. Now, number 4, it says how many molecules of H2O are present in 35.8 grams of H2O. So, once again, we are going to start with what we're given. Bye. We start with what we're given, 35.8 grams of water. Now, what am I going to do with this?
So what's the next conversion factor?
Yeah, what am I gonna do? Help me out, guys. I got amnesia. How do I solve this problem? What do I do next?
Do we find the molar mass of H2O?
Yeah, very good. Absolutely. We find the molar mass of H2O. But you know, before we even do that, let's set down our units. Because you're not wrong. You're definitely not wrong. What unit goes on the bottom of this first conversion factor?
Grams.
Yeah, grams of.
H2O.
There you go. Grams of H2O. What goes on the top? What unit?
Moles.
Moles. Yeah, because you can't necessarily go from grams directly to molecules. I mean, I suppose you can if you know what the relationship is, but it makes more sense logically to go from grams to moles. And then once we have moles, then we can go to the next step. What unit's going to go on the bottom of the next conversion factor? What do you think?
Moles. Isn't it?
Yep, absolutely, moles of water. Hmm. And then what can I convert moles of water to then?
Molecules.
Molecules of water. Very good.
I just wanted to make a comment about Ethan's chat, and he presents the molar mass of water as 18 AMU, which is the units is not quite accurate. I mean, the 18 is correct. You calculated it correctly. But the unit is not absolutely correct. We cannot say that we have 18 atomic mass units of water. Does anybody have, or 18.02, thank you. Does anyone have any idea why it would not be accurate to say 18.02 AMU of water?
Yeah, why would you not use the unit AMU? Ethan's like, I don't know.
I was I was thinking that I was thinking it was a numerical problem because the number 18 would actually be wrong. But
Oh no, the number 18 is absolutely right. 18.02
okay,
is correct.
that's good.
Yeah, exactly. There you go. Like, you know, forgive me for teasing you, Ethan. You're a really good sport, and I'm really glad that you just jumped right in there. But yeah, absolutely. No, it's because AMU refers to the mass of one single molecule, not the mass of a mole. And it is kind of like semantics in a certain sense, but it's also more than that. Um, 1 mole is 6.02 times 10 to the 23rd particles. So 1 mole is not 18 AMU. 1 mole has to be 18.02 grams. Does that make sense? Cool. And then, of course, 1 mole also happens to be equal to Avogadro's number. Anytime we go from molecules to moles, that's going to be 6.02 times 10 to the 23rd. 10 to the 23rd. There we go. All right. And now all I have to do is multiply everything on top and divide by everything on bottom. And what do I get? 1.20 times 10 to the 24th. Excellent, excellent.
Yes.
Ethan, you are on point.
Yes.
1.20 times 10 to the 24th. And that is molecules. molecules of water.
Is
Okay,
it clear?
absolutely.
Is it clear to everyone how these problems can be very straightforward? In other words, going from grams to moles to number of particles back and forth. So you should be able to do these operations in your dreams, going back and forth between grams to moles to number of particles, because really once you start writing out the known information and driving it with the dimensional analysis, you cannot go wrong.
Hmm. And actually, that's a really good point. I want to actually take a second, based on what Professor Neely was saying, and draw y'all a cute little map here. I'm going to draw you a cute little map right here. I like maps. So I'll put one here, put one here. Oh, come now. Give me another circle.
It doesn't always do what you want it to do.
It doesn't always do what I want it to do. Ah, you telling me I have to pick one each time? Okay, let's try this again. And then I'll do one more. Whoa, there we go. So, cool. So here's the thing. This, if you have grams of a substance, call it A. If you have grams of A, there's really only one thing that you can do, and that's convert to moles of A. And if you have moles of A, you can convert to atoms, or if it depends on if it's a atom or a molecule, but atoms or molecules of A. Okay? However, the cool thing is you could actually convert moles of A to something, moles of something else. And we're going to actually show you how to do that in just a little bit. This is what might be referred to as a stoichiometry map. Okay? There's a two-sided arrow here. You can go forward and you can go backwards. You can go from moles to grams or grams to moles. You can go from moles to atoms or atoms to moles. And you can go from moles of one thing to moles of something else, or vice versa. So what's the conversion factor for this? How do you do that? Well, it comes down to this. To go from grams to moles, I need the molar mass, right? And specifically, if I'm going from grams to moles of a substance A, whatever A happens to be, I need the molar mass of A. Likewise, if I want to go from moles to atoms or molecules, for that, all I need is Avogadro's number. Huh, not Avogadro's money, Avogadro's number. There we go. And that's basically the 6.02 times 10 to the 23rd. And if I want to go from moles of A to moles of B, I can either do one of two things. I need either coefficients from a balanced equation, or coefficients from the balanced equation, or I need to use the atom to molecule ratio. That a molecule might have. So, like for example, for H2O, I could say I could say something like, and this would just be an example. For water, I could say there's two atoms, or since there's two atoms of hydrogen in every one molecule of H2O. Oh, whoops, What am I doing? Minus, minus. Okay. Make me a subscript, will you? Ah. Oh, you know what? Fine. Do that way. H2O. Okay. Because there's 2 atoms in every molecule of H2O, that means I can also say, because an atom to molecule ratio is the same as the mole ratio, because mole is just 6.02 times 10 to the 23rd. So in other words, if I need 2 dozen hydrogen atoms to form 1 dozen water molecules, then I can say 2 moles of hydrogen atoms would form 1 mole of hydrogen molecules. So I can do a mole to mole ratio like that. So what did I do? Did I do something? There we go. Okay. I think there might have been a question.
No, I guess you were getting a lot of compliments for the map.
Oh, thank you. Thank you. I don't presume to compliment myself, but my friends say I certainly can draw a map. No, I'm just kidding. Shame on me. So this basically is, that's basically the idea. This atom to molecule ratio can allow you to convert from one substance to another. So this is the map. So you can go from any place on this map to another using these conversion factors, either the molar mass, or Avogadro's number, or the atom to molecule ratio. And we'll expand this map later on in just a couple chapters. But for now, this will work for our purposes. Cool. Let's go ahead and slide ourselves back over to our fun little problems. Now it says, determine the percent composition. Actually, does anybody need any more time with this, or can I move over to the problem? Is that okay?
I think the map really helped clarify what's being done.
Okay. So I'm hearing it's okay to move then?
Yes.
Okay, cool. Time. We'll move over. Okay. So determine the percent composition of ammonium nitrate. So you thought all that naming and writing of formula stuff was something you were never going to have to look at again in your life, didn't you? No, probably not. But it's going to come back to haunt you sooner than you might have expected. What is the formula for ammonium nitrate? Would one of you fine students like to write down the formula for ammonium nitrate? You can write it down right here.
They wrote it in the chat.
You wrote it in the chat. Okay, fine.
Sorry, I did that too fast. My apologies.
No, it's okay. It's very slightly incorrect, though. Ah, there you go. Good job, Alicia. Rock on. There we go. Excellent. Now, I like how you moved it down just like a little bit. Like, and just for the, and you're absolutely correct. It's corrected. Just for the purposes of clarity, I'm just going to go ahead and write this out because I want to show the subscript here. So this is NH4 NO3. Because subscripts tell us how many atoms, superscript tells us the charge. Okay, so I'm going to go ahead, and when I'm doing percent composition, I think that the easiest thing that you can do when doing percent composition is to go ahead and calculate the molar mass and show the complete calculation like I did over here with this thing up here. So I'm going to actually do that for the NH4NO3. So I'll start with my nitrogen. How many nitrogens do I have in this formula?
Not nickel, but not.
Oh yeah, this is not nickel. Sorry, these are dots.
Oh, okay. Thank you.
Yeah. So 2 times the molar mass of nitrogen. Molar mass of nitrogen is 14.01. So that's going to give you 28.02. Boom. And then I have hydrogen, and there's a total of how many hydrogens? 4, yep, good. So I'll multiply that times 1.01. And then I have oxygen. Looks like my little friend is with me. My son just walked into the other room. I'm a little bit concerned about what he's doing.
Oh,
So-
he's a character.
Yeah, he is. Um, my son is autistic, and his favorite thing to do in the whole wide world is unroll toilet paper and shake it all over the house. It is sometimes hilarious what we wake up to. Okay.
I just loved his confidence, you know, I mean, just like for a 6-year-old kid to be that confident was, I can't get over it. He's amazing.
So we got 3 oxygens here too. And 3 oxygens, so 16 mass each one. Okay, so now I'm going to go ahead and do 4.04. That's 4 times 1.01 is 4.04. And then 3 times 16 is 48.00.
Excuse me for one moment. I have to step out. I will be back shortly.
No problem. Absolutely. Thank you, Ethan. You're 100% correct. Okay, so Rosanna, you asked a really good question. The truth is, if you look at any source for oxygen, if it goes to 3 significant figures, it'll say 15.998, or usually it'll say 15.998, or it's like 15.99. Sorry about that. 15.998 or 15.9998. I'm not sure which one it is, but in either case, that will round to 16. In either case, that will round to 16. Okay?
Excuse me?
So, so yeah, you'd want to use 16 in that case. So now you have 8. Ethan told us this up. We get 80.06. Oh, yeah. Did somebody have a question? I'm sorry.
Yes, about the 16 and 1.01 and 14 come from where?
Those are all from the periodic table. If you look on the
Oh.
periodic table underneath the nitrogen, you'll see the average atomic mass of nitrogen, and that's what we're going to use here, and that would be 14.01. Hydrogen will often be written as 1.008 or 1.01, or sometimes it'll be 1.0079. It just depends on how accurate, to how many decimal places your depends on how accurate or to how many decimal places your thing is, your periodic table is. But yes, those are all from the periodic table. Does that
Okay,
help?
thank you so much.
Yeah, no problem. Thank you for your question.
Yes.
It's a good question. All right. So, and the reason why doing the molar mass this way is so super helpful when calculating percent composition is that you already have the mass attributable to each element. From here, I can take the mass contributed by each atom and divide it by the total mass times 100%. So, for example, if I want to do the percent of nitrogen, percent nitrogen is going to be 28.02. Divided by 80.06 times 100%. And that's going to give you the percent nitrogen. And then, so what does that give you for percent nitrogen? 35%. There you go. And so that'll be 4 significant figures. So well done. 35.00. Sorry, that 3 is kind of terrible. There we go. And then you would do the same, that's 35.00% nitrogen. And then I would do the same thing for hydrogen. The only difference is I would use hydrogen's mass, which is 4.04, and I would divide that by the total mass, 80.06, and then times 100%. And that'll give me my percent of hydrogen. And then I can follow that up with the 48.00, the mass attributable to oxygen. Divide that by 80.06 times 100%. And that'll give me the percent oxygen. And what you should notice if you calculate each of those is that the percentages should add up to 100%. Sometimes due to rounding, it'll be like slightly off, it'll be 99.99 or 100.01, but it should effectively be 100% that it all adds up to. Did anybody calculate the percent hydrogen? Excellent, 5.05. 5.05. 5.05%. And then, what about the percent oxygen? 59.96, very good. All right, let me go ahead and have you guys take a stab. Take a stab at the percent composition of magnesium acetate. Now, although percent composition technically means the percent of each element within it, so the total percent composition of ammonium nitrate would actually consist of these three numbers. But why don't you just go ahead and do 1? So I want you to calculate the percent composition of oxygen in magnesium acetate. So tell me what the percent oxygen is in magnesium acetate. Oh, sure, absolutely. Let me move that over. Oh, Ethan, you're wrong, by the way.
Oops.
Bum, bum, bum. I'll leave you to contemplate why. Of course, that's assuming that I did the calculation correctly. I could be full of it.
Or Ethan maybe off by, oh, there you go.
There you go. I think that's right.
You were just off by a factor of 2, not too far away.
You forgot to multiply those oxygens by 2, didn't you?
I did. But that's the dumb thing is I didn't because I got the correct mass. Because I got the percent right the second time. I just...
yeah. No problem. All right, let's go ahead and take a look. You wanna show them how it's done, Ethan?
Sure.
Wow.
How do I do that?
Show what you did. Well, you can select. You see where my hand? Can you see what I'm doing on the board?
Yes.
Yeah. So click on that little pen eraser tool. It's a little squiggly line on the side, on the left-hand side, and then you can go ahead and draw to your heart's content and show us what you did.
All right. Well, it was pretty messy to be honest, but I knew that acetate was. Oh, geez, that's terrible. C2 H3 O2 minus. So I knew it was negative. And I knew that the charge of magnesium is 2 plus. So I knew this needed to be of a factor of 2. So it was magnesium C2 H3. Jesus, it's horrible. O2. And then 2 out here.
It's tough to draw on this.
Yeah, man, I'm not very good at it yet.
Takes practice.
I guess
Well,
so.
at some point I'm going to show you a little trick for how you can actually slow down your mouse. It actually makes it a lot easier to draw.
Why wait?
Oh,
Right.
well, basically, do you have Windows 10?
Oh, unfortunately, yeah.
Yeah, that's my thoughts about it too. Windows 10, just go ahead and right click on the Start menu, and then click on Mouse, and then type in or search for programs or search settings or whatever. And under that search button, just type in mouse settings or just mouse.
And you just slow it down. Gotcha. Well, I'll do it afterwards. I'll finish
Okay.
this.
There you go. I'll help you out a little bit with this.
Thank you. It's taking me a little bit.
That was just 1.01 times 6, so that's 6.06. And add them up. Bam. What did you get for the total? It was like 142,
Yeah, 142.41.
142.41.
Yeah, so 64. That's a 4, not a plus.
Nope, I know. You're good.
Awesome.
Times 100%, right?
Yep.
And there we go. Right on, man. Excellent.
Thank you. I should have shown you how I did it the first time.
And then, so that would be, so that basically gives you the 44.94%. Excellent, excellent. Hold on, and note that this is actually, technically speaking, 64.00, which is why when you add it together and you have that here, you will get 4 significant figures for your answer. Cool. So now that you know how to do it, percent composition, we can jump to empirical formula. And a lot of times you'll be asked to solve for what the empirical formula is from the percent composition. So instead of solving for percent composition, you'll be given percent composition, and you have to solve for the empirical formula. Well, first of all, we have to understand what the empirical formula is. And so I'm just going to give you a brief definition here. Empirical formula, lowest whole number ratio. The lowest whole number ratio of atoms for a molecule. So for example, what does that mean? Well, for example, if you have like a compound like benzene, which is C6H6, benzene is C6H6, so that's a real compound. The empirical formula would be, I'll just abbreviate it, EF. The empirical formula is CH, because the lowest whole number ratio is just 1 to 1. This over here, this would be referred to as the molecular formula. Can't spell today, apparently. That's a U. Formula. My goodness, what is that trash? Alright, I'm just going to type. Okay. Ratio. There we go. And then I'm going to go ahead and move this. So the empirical formula is useful not in and of itself. If you have the molecular formula, the empirical formula is not all that useful. But a lot of times the information you're given on a substance, if you know nothing about a substance, okay? If you know absolutely nothing about a substance and you start running tests, you can use those tests to determine the empirical formula. It's not that the empirical formula is useful in and of its, or it's not that, and you can use the empirical formula to determine the molecular formula along with some other information. So it's not so much that um, not so much that the empirical formula is useful if you already have the molecular formula, but it is useful if you don't
If you
have the
haven't,
molecular formula.
right, if you have like an unknown liquid. And so to your point, Professor DePass, if I mean, in practice, nobody's ever going to use CH to describe benzene. Everybody's always going to use C6H6. But however, as Professor DePass was saying, if you have an unknown and you don't have any information about it, and you have just, for example, the percent composition, just a very practical example is, suppose you have a unknown liquid that is clear and colorless, and you've determined the percent hydrogen composition, and you've determined the percent oxygen composition, then you use that to find the empirical formula. So that's where its practice comes in.
And there are other tests that you can do then to determine the molecular formula once you know what the empirical formula is. So,
Yes.
here, let's go ahead and take a look at this example. So let's say we run this in a mass spectrometer. A mass spectrometer will actually give you the data of percent composition if you run a sample through it, okay? So let's say we run a pure sample of an ionic compound into the mass spectrometer, and it gives us this data. It looks like that the approximate percentages of each one of the elements present are 26.52% chromium, 24.52% sulfur, and 48.96% oxygen. Well, what you can do with this is you can calculate the empirical formula by assuming that you have 100 grams. So notice that step 1 here says assume you have 100 grams. This turns all your percents into grams. Then we convert each of our grams to moles. So we're going to use the skills that we just learned from the previous part, and we're going to start converting each of these grams to moles. So we'll say 26.52 grams of chromium, and then we'll multiply that times the conversion factor, and we're going to convert these grams to moles. So grams is going to have to come on the bottom, and we can convert grams to moles directly using the molar mass. Based on my cool little map I drew, so proud of myself. Okay. So, shame on me, I get ridiculous at this time of night. All right, so then we can calculate the moles of chromium. Now, we can do the same thing for sulfur. I'll start with my 24.52 grams of sulfur, because it said I had 24.52%. And then I'm going to go ahead and convert. The mass of sulfur is 32.065. I'm breaking my own rule here, which is always put your units first. Don't break my rule. I'm allowed to break my rule. Do as I say, not as I do. Okay, so grams of sulfur to moles of sulfur. Shame on me, I feel like a politician when I say that. Do as I say, not as I do. Shame on me. Or a bad parent. Okay. So 24.52, and then you divide by 32.065, that's going to give you moles. All right, and then we'll do one more thing. We'll do the same thing with oxygen. We'll take our 48.96 grams of oxygen. And we can convert the grams of oxygen to moles of oxygen. 1 mole of oxygen is equal to 16 grams based on the periodic table. I know it's 16.00, but I'm getting lazy. It's late. Now, I'm going to go ahead and calculate the moles of each one of those. So what does that give me? I'm counting on your fast calculation skills, Ethan. Hook me up. What do we got?
For chromium, I get 0. Oh, wow, he already did it.
Is that for oxygen?
Yeah. So for
I think so.
I need 4 sig figs, by the way.
okay, 0.5100.
0.5100. Okay, that looks good. That's moles of chromium. And then what do how much do I get for sulfur?
For sulfur, we get 0.7647. 0.7647.
Getting a little bit ambitious on those sig figs. That's 5, buddy.
Yeah.
Zero.
Wait a second. Did I?
Yeah. You add that extra 0 at the end. That would be 5.
Wait, so what about the 0 in between the decimal and the 6.5 on the sulfur? Is that not a sig fig?
It is a sig fig, but you always go with the lowest number of sig figs, and
Oh my word!
6.4.5.
How did I do that? Jeez.
It's getting late. That's why you did that.
It's not late for these kids. They stay up till like, I don't know. Who knows?
Midnight, 1 a.m.
All right. All right. So now once you have the moles of each one of these, here's what you need to do. You need to divide each number of moles by the lowest number of moles. So this is the interesting thing. You're going to divide each number of moles by the lowest number of moles. Okay, so what's the lowest number of moles between all these three?
Chromium's point.
Chromium. So if I divide the 0.5100 by 0.5100, of course, that's just going to give me 1, right?
Yes.
What do I get if I divide 0.7647 by 0.5100? Yeah, roughly about 1.5. I know you're right. It's just going to be 4 significant figures, but we're going to round this to a whole number or at least an easily identifiable fraction. And then what do I get if I divide 3.060 by 0.51? 6. There we go. So this is going to give me 6. So what this does is this actually gives you the empirical formula almost, because if you have a fraction like 0.5, I need this to be the smallest whole number ratio. Right now I have a 1 to 1.5 to 6. So now to get a whole number ratio, what do I have to do? The current ratio. Go ahead.
I was going to say, I think Ethan is having too much fun. He's thinking about pursuing chemistry.
There you go. Multiply the ratio by what? What do I need to multiply by to get a whole number?
3, right?
Well, not 3, because 1.5 times 3 gives you 4.5.
Oh, sorry, 2.
But 2. So I'm going to go ahead and multiply this, but everything has to get multiplied if we're going to multiply. So this is going to be a 2. And then 1.5 times 2 is going to be a 3. And then 6 times 2 is going to be a 12. So this is a 2 to 3 to 12 ratio. And so then I realized, okay, well that means that this is Cr with a 2 chromiums, S3, O12. So Cr2S3O12. But you know what the interesting thing about that, if you recognize that that 3 to 12, that's like a 1 to 4 ratio between the sulfur and the oxygen. I wonder if that is a polyatomic ion. Turns out it is. This is chromium SO4 3 polyatomic ion. This is chromium 3 sulfate. So the truth is, this could actually be, because chromium can react with sulfate. Chromium can react with sulfur and get chromium 3 sulfite. It can get chromium 2 sulfate. You can get a lot of different things depending upon what you're reacting with and under what conditions. So there's a lot of different possibilities. So let's say, for example, you were running a lab where you were trying to produce some compound with chromium, sulfur, and oxygen, and you have no idea what this substance was. It's just this black, tarry stuff or whatever. You went ahead and threw it into the mass spectrometer, you get these percent composition, and you're like, okay, well, what does that mean? Let's figure it out. So you do this calculation, and you get the empirical formula, and you're like, oh, this is chromium 3 sulfate. That's what we produced. And then you can write down all the different properties it has, which is kind of cool. No, you're absolutely fine. So if you wrote the empirical formula, like for purposes of like if you were given a question on a test or something, if you wrote your answer like this, the chromium Cr2S3O12, that would be perfectly acceptable. That'd be 100% correct. However, bonus points if you recognize that it was this. Cool? I think that's kind of fun. We play as we're analytical chemists, scientists, finding out the unknown. And this is also, coincidentally, I mean, this type of analysis is what you can use to actually figure out what poisons are present in a body or something like that, isolate different compounds, run different spectral analysis on various different samples. There's a lot, and there's some more advanced techniques that eliminate the need to go all the way down to the atom. But this is the type of kind of cool stuff you can do as a forensic chemist, exploring and searching, trying to figure out what exactly is present and where it comes from. All right, now we have the empirical formula from experimental data. We don't have a whole lot of time here, so I might actually go ahead and skip ahead a little bit.
Could you just tell us how to go from molecular formula or from empirical formula to molecular formula?
Yes, that's definitely what I want to do. By the way, just as a side note, looking at how to do this from experimental data, like you could also be actually weighing this stuff. Like there's a lab that students sometimes do in class when you actually have a lab and it's not like all online. If you take 0.245 grams of powdered copper metal and you roast it in oxygen, you get a product, and the product weighs this much. You want to figure out what the empirical formula of the compound is. So you do basically the same thing that you did with the previous problem. You can convert the 0.245 grams of copper to moles, but you can also then, since the product is composed of oxygen and copper, to get the mass of oxygen that was added to it, CU question mark, O question mark, I don't know what these question marks are, I can subtract the mass of the copper from it, the 0.245, and I can get the grams of oxygen. And now in this case, I think it's the 0.059. And then once you had the grams of the oxygen and the grams of the copper, you could convert each of those to moles, just like you did in the previous problem, and then divide by the lowest number of moles. Now let's say you wanted to find the molecular formula, okay? So let's say, for example, I'm going to give you an example. Say, for example, you determined that the empirical formula for a compound was CH2O, okay? So that was the empirical formula. You determined that this was the empirical formula, and you did it from a percent composition like the one that we did in the first problem. So here's your empirical formula, CH2O. Using a separate analytical technique, let's say you discovered that the molar mass of this, and there's different ways to get the molar mass. And admittedly, a mass spectrometer is also another way to get the molar mass, but there's different ways to get the molar mass. But the molar mass, let's say the molar mass was approximately 180. Okay? Well, if I wanted to figure out what is the molecular formula, if the empirical formula is CH2O, what's the molecular formula if the molar mass is 180? Well, here's how you solve that. First of all, you need to be given the molar mass or have some way to determine the molar mass. So either from experimental data like a mass spectrometer or something like that, which you're not going to get in a Chem 1411 class. They're just going to give you the molar mass. And then you need to calculate the empirical formula mass if they don't give it to you. If they do give it to you, great. Then you divide the molar mass by the empirical formula mass, and to get a whole number multiplier. Sorry, calculate the empirical formula mass. I thought it said calculate the empirical formula. But calculate the empirical formula mass. So if I take the mass of the CH2O, well, that's 12 from the oxygen plus 2 for the hydrogen plus 16 for the oxygen, right? That's going to give me a grand total of 30. So now then I can do step 3. So step 1, step 2. Now I'm going to do step 3. Divide the molar mass by the empirical formula mass. So I just take the 180 and I divide it by the empirical formula mass of 30. And that gives me 6. So that means the original empirical formula has to get multiplied by 6 to give me the molecular formula. So I multiply each number of atoms, the number of each atom in the empirical formula, by the whole number multiplier. And that's going to give me C6H12O6. Exactly. It's sugar.
Yay, good job.
So that's how you can determine the empirical formula, or the molecular formula from the empirical formula and the molar mass. Well, we didn't quite get to our last problem, but that's totally okay. The complete guide is, the completed outline is up on our website. I just want to show something. Where did you get the numbers that added up to 30? Oh, it's from the periodic table. So the molar mass of carbon is 12. 2 hydrogens, each hydrogen is about 1. So 1 times 2 is 2. And then the molar mass of oxygen is 16. So those numbers came from the periodic table. No problem. So let me show you something really quick. I want to show you something pretty cool. I'm going to share my screen with you. Da, 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 da. Okay. So if you go to our website, If you want to check out the rest of the workshop outline and the completed workshop outline, you can just go to our website. You can Google or type in any search engine, TCC space SE space science, and it doesn't matter if it's capitalized or lowercase. It'll pull up our website. You could also just click on the link from the emails I've sent you, and that'll pull up this, and you can go to 1411. Chemistry 1411 under workshops and events. So click on workshops and events and then Chem 1411. And if you scroll down to the bottom, it has completed outline, workshop and empirical formulas. The cool thing about this is it has everything worked out with all the work shown and all the notes filled in. So see how nice and pretty that looks? That looks pretty. All the work is shown, shows all the work, makes it so nice and clean. So all you have to do is you can look that up from our website. I will also have the video posted below this video session that we did here, in case you want to reference back to it. But you can also check out some super cool practice problems. I have awesome practice problems up on 1411. If you just go to Chemistry Web Resources, go down to 1411, chapter reviews, practice problems, here we go. And if you scroll down to the section where it says chemical equations, stoichiometry, and combustion analysis, there is a section on percent composition with the answer key. There's empirical and molecular formulas. There's practice and empirical and molecular formulas and answer key. It doesn't let me highlight just that. There's percent composition, empirical formulas, and molecular formulas. And so once again, all the answer key has all the work shown. So that makes it easy. It's a little bit harder to see, but you can strain your eyes, you'll read it. But then I also have this really cool combustion analysis problem. And this is a little bit more advanced. It's still the same stuff that we were working with, but the analysis is a little bit more complex. But I have this beautiful answer key that goes along with it that shows you every step and explains what the step is for, why you do that step. So, and there's like sunshiny rainbows around the correct answer, so you know exactly what the correct answer is. So it's pretty cool. And just in case you wanted to review some videos, like get a little bit more ahead on, not this one, on some of those things that we didn't quite get to, you can go to video tutorials, and I actually have under molecules, compounds, and chemical equations, this third one. I do actually have some very cool stuff over molar mass, percent composition, and calculating empirical and molecular formulas, including a combustion analysis problem. These are the really hard ones. So, very cool stuff. I know that's kind of like drinking from a fire hose, but I hope that helped. Any questions before we go? Awesome, awesome. And also, don't forget, you can definitely come by anytime to the Science Learning Center and get free one-on-one tutoring with one-on-one tutoring with me or one of the other chemistry tutors. You just, instead of clicking like one of the workshops, you just click on the SE Science Learning Center tutoring room, and somebody can be with you right away. It's on demand. You don't have to make an appointment. You can just feel free to drop by anytime. Well, thank you so much, and you all have a wonderful evening.